Okay, welcome everyone to today's seminar. Today we're very happy to have Alexey Milekhin from Princeton and now Santa Barbara, who is going to tell us about humanly traversable wormholes. Alexey, the floor is yours.
Okay, thank you. Yeah, today I'm going to talk about humanly traversable wormholes. My talk will be based on two papers. The original construction from 2 years ago, which first proposed using Casimir energy to build traversable wormholes. And then the second part of my talk will be based on this recent paper for how to embed those into Randall-Sundrum model and make them humanly traversable. So what are the traversable wormholes? So this is a picture just of a wormhole. So we have two space regions which are connected by a handle. And we say that its wormhole is traversable if an observer can actually travel through the handle. And it is humanly traversable if a Homo sapiens can travel safely. And I would like to point out that safely means it's safe for both the Homo sapiens and the wormhole. Wormholes are actually quite fragile too, but in a different way. I will explain it in a bit. So in my talk, I would like to answer two questions. So do such objects exist in classical Einstein gravity in 4 dimensions without exotic matter? And again, in just in one slide, I will explain what I mean by exotic matter. And the answer is yes. And the second question is, can they be made humanly traversable with matter which is roughly consistent with the current observations? And the answer is yes. Although in my case, we did not include very stringent constraints, but at least the matter contact we're gonna talk about it makes sense. Okay, let me explain what I mean by not exotic matter. So these are the familiar Einstein equations where G Newton is just a constant, which is in our universe as this. And T mu is the stress energy tensor of matter. So the properties of the matter determine the properties of the space-time. And the traversable wormholes requires the so-called negative energy. And the physical reason for this is that there are two spheres inside the wormhole. It first shrinks and then expands. And so various theorems in Einstein gravity prohibit this unless we have negative energy. And precisely, let me explain what I mean by this. So if we have a simply negative cosmological constant, in some sense it does lead to negative energy, but this is not what we actually want. What we want is a violation of the so-called average null energy condition. So it means that we take non-extendable null geodesic, integrate the corresponding null component of the stress energy tensor along this null geodesic. And so this is a neck, and for a traversable wormhole, this quantity here, it should be negative. And a neck is violated by the famous Casimir effect. So I should point out that all classical matter satisfies this requirement. So, but the Casimir effect, it's quantum, so it actually violates this. So let me remind you what Casimir effect is by an example. Suppose we have a massless fermion on a circle of length L, so just in 2 dimensions, and we can impose antiperiodic boundary conditions and compute the difference between the energy on the circle and energy in flat space-time. So this energy difference is actually UV finite, and it equals to this. It's negative, and it leads to the following non-null component of the stress energy tensor. So this is precisely what we want. And notice that this quantity is proportional to the Planck constant, so it's small, so it's a quantum effect. But I believe that it has been actually verified experimentally. So one maybe technical comment is that in our case, the space-time will be curved, but the Casimir effect can be generalized to this case as well. We just need to take into account the conformal anomaly. So this is again the picture of a wormhole, and I did in this case when we have a wormhole, we have one cycle which is not contractible, and this is very similar to the case with these fermions living on a cylinder, because they can go around this cycle. So when we introduce it, if we have matter, then it will produce a Casimir effect and produce negative energy. So this is the idea, to use this negative Casimir energy to construct the wormholes. But there is a problem, because we need a lot of matter, because not only we have to compensate for the Newton constant, but also we have to compensate for the Planck constant as well. And so one observation is this: we can actually use magnetically charged black holes for this purpose. So this was proposed in our paper with Juan and Fedor. Essentially, if we take magnetically charged black holes with charge Q, then it has been known for some time that free Dirac fermions in this background, they support two-dimensional fermionic modes. This is known as Kalin-Rubakov effect. It has been known since 80s, and it's valid not only for black holes, for monopoles as well. Perhaps I should clarify why are they two-dimensional. Let me just draw a picture. So this is, say, a two-sphere, and we have a magnetic flux coming in all directions. And roughly we have one fermionic mode per unit flux. So it means that this fermionic wave function is in fact localized on a scale of radius divided by the square root of Q. So if we go to the energy scales, to scales above this length, let's call this LB. Then we can essentially neglect the inner structure of this fermionic wave function, and we can just concentrate on its movement in the radial direction. So essentially they become effectively two-dimensional. So are there any questions on this point? So, okay, actually this equation, we should remember this because it will appear later in our discussion when I will discuss holographic matter. That the point is that below a certain energy scale, we can treat these modes as effectively two-dimensional, and they will have two black holes, then they can propagate along the magnetic lines. This is actually even observed in the on Earth, because you know that there are polar lights, because the charged particles from the outer space travel along the magnetic lines of the Earth. So you can see them in the poles. And this is exactly the thing which can happen between two magnetically charged black holes. These massless modes will propagate along the magnetic lines. And this is why it's good for us, because it means that all these excitations, they won't just spread around in 4 dimensions, but will travel exactly along this effective 2-dimensional cylinder. But there is a problem with this, because if we assume that even if we have some dark sector with this dark U1 gauge field, it requires an enormous number of fermionic fields in order to make it macroscopic and humanly traversable. So number of fermionic flavors should be 10 to the 52. So it's extremely unlikely that there will be a dark sector with this number of weakly interacting fermions. It means that one will have to tweak the coupling constant to be smaller than this number, because these fermions, they can travel in loops, and so the effective coupling constant is in fact multiplied by this, and it would be true even for gravity interactions. So such big number of fields would mean that they would strongly interact with gravity well below the TeV scale. So this is just does not make any sense. So then I guess one natural idea is that what we try to describe the matter holographically as well. So we say that we have a 2-dimensional CFT described by 5-dimensional Randall-Sundrum, and the question is, what happens in this case? Do we still have these massless modes or not? So this is the motivation, and this is the plan of my talk. So first I will review this purely 4-dimensional construction of traversable wormholes. Then I will review the Randall-Sundrum model and how the 2-dimensional CFT arises in this case. And then finally, I will discuss human traversability and just summarize. Okay, this is the plan for the rest of my talk. Are there any questions? Okay, let me then continue. So this is roughly the sketch of the 4-dimensional geometry we will be talking about. So we have two black holes separated by a distance d between each other, and they are joined by a wormhole throat of length L. And the geometry inside it will be AdS2 cross S2, which we will have to glue to the near horizon region of these black holes. So we will essentially, outside the black hole, the metric will be just Reissner-Nordstrom. Inside the throat, it will be AdS2 cross S2. And there will be a gluing region where we actually have to do some work and patch with these two metrics. And the Casimir energy will be important in patching in this gluing region. So one important comment is that we construct so-called long wormholes, meaning that the distance L is actually larger than D. This is why the picture is drawn like this. So these wormholes, they are not good for science fiction, because it actually, for a distant observer, it's actually faster to travel along the flat space-time and not through the throat. But this is not accidental. In fact, these short wormholes where L is less than D, they can be converted into time machines. So you can actually travel, you can tweak them a little bit and actually travel back in time. So this is not good. And moreover, short wormholes violate the so-called achronal average null energy condition, which is less strict requirement. And what it means that this is essentially the same as INEC, but now we require that this inextendable null geodesic is achronal. And I will, in the next slide, I will illustrate what achronal mean. And as far as I know, there are no violations of this achronal INEC, and I believe it has been proven for flat Minkowski space. So even on the quantum level, there are no known violations of this, which is perhaps not surprising, because if it is violated, one can couple this theory to gravity and construct time machines. So achronal means that this null geodesic is not intersected by a time-like geodesic. So for a cylinder and the null line winding along like this, it is not true. So this green line is not achronal, because you can just stay at one point in the cylinder and travel along this blue time-like geodesic and intersect this null line twice, or in fact, infinite amount of times. So let me now describe the precise gravity solution. So we consider Einstein gravity and U1 gauge field. It has the Reissner-Nordström solution, where instead of the electric field, there is a magnetic field. So Q is the magnetic charge. So the metric is exactly Reissner-Nordström. It's just A now describes magnetic field. So it has, this solution has non-zero temperature and entropy because there is a horizon. So in fact, we assume that this U1 gauge field, it's not strongly coupled. So G4, it can be further one or less. So the magnetic charge has to be huge. And it has to be huge for the following reason. So we study these black holes in the near extremal regime, when all the mass is given by the magnetic field. And in this case, the horizon size is determined by Q. So the horizon size is Q times L Planck. So if you want it to be macroscopic, then Q has to be large to compensate for the Planck constant. So the Planck length is 10 to the minus 35. So because of this, the magnetic fields will be huge as well. And there was a recent paper by Huan where he discussed what are the physical consequences of having such strong magnetic fields. So in this regime, the temperature goes to 0, but entropy is not, because one can check that the area of the horizon tends to some constant value, and it has some dynamical consequences. I will talk about this in the conclusion section. So this is how it can be illustrated. So outside the black hole, there is a flat space-time. The region around the horizon has a size of order RE, and there is a long throat described by ADS2 cross S2 near the horizon. And so ADS2, it is not, so there are many different patches of ADS2. Precisely the one we have outside the horizon is the Ringler wedge, described in red in this point. And this is a simple exercise. One can rewrite the Reissner-Nordström metric near the horizon in this form. So this is just two spheres of constant radius. And this is a Ringler patch. And so what we want to do is we want to take two such Rindler patches and glue them to a global ADS2, which is in this picture is green. So we in this gluing region I mentioned, where we need the Casimir energy, we need to glue these two metrics together. Yeah, this is the proposal, to make the geometry inside the throat global ADS2, and in the near horizon region, it's ADS2 in the Rindler patch, and then we will have to glue them together. One can actually wonder if it is just different patches of the same geometry, why do we need matter at all? And the answer is this, is that we also have a two-sphere. And in order to, in fact, technically, in order to patch the two-sphere part, one needs the Casimir energy. This is just a very technical comment. So the only input, in fact, we need is that we have an effective two-dimensional CFT, which roughly corresponds to fields traveling in the radial direction. So we say that near the horizon, we have a stress energy tensor, which is spherically symmetric, and which is determined by this central charge. This coefficient of 8, it takes into account the conformal anomaly on ADS2. So this would be the stress energy tensor component if we indeed have a Casimir energy corresponding to fields which are spherically symmetric on ADS2. Oh, sorry, spherically symmetric on the S2 part and travel along the ADS2. Then we take the following metric in the throat. So this is just a small deformation from the global ADS2. And in the near horizon region, we take a metric which is close to Reisner-Nordstrom. And then we have to patch them together near the horizon and near the boundary of ADS. So in fact, one can just take this stress energy tensor and take this ansatz for the metric, plug it into your favorite program of computing the Einstein tensor, and find the solution. So I will not go into the details, but this is how the geometry will look like. So are there any questions maybe?
I had a question. So
Please.
2D CFT is in the bulk and is used to probe the geometry to be almost identical to ADS2 cross S2. Is that the?
Sorry, could you please repeat your question?
Why are we why do we have as an input a 2D CFT with some central charge? Is it because we require to probe the geometry in the near horizon limit to be ADS2 cross S2?
So CFT, it's maybe I should have mentioned this before when I was talking about the Casimir energy. So the Casimir energy is Casimir energy is suppressed when the fields are massless, or sorry, when the fields are massive. So for massive fields, maybe I can just write an equation to make it more precise. So if mass is equal to 0, the Casimir energy is proportional to 1 over L, where L is the length. But for non-zero mass, the energy is exponentially suppressed. So this is what this is why we need massless fields. And for example, I said earlier that previously we considered just free fermions in the background of the two black holes. And it's important these are fermions because only fermions have zero modes in this background. If you take scalars, then they will be actually gapped. So they're even if you take a massless scalar in this magnetic background, it will have a mass proportional to the magnetic field. But with the spin 1/2 particles, this magnetic part, this correction to the mass from the magnetic field is cancelled by the interaction between the spin and the magnetic field. This is why we have precisely zero modes. And this is, gives rise to a lot of zero modes. And this is why they produce a non-negligible Casimir energy. But here I'm not saying that I have some free fermions. I'm just assuming that I have certain effective two-dimensional matter traveling along the radial direction. And I'm assuming that it produces spherically symmetric stress energy tensor near the horizon coming from the Casimir effect. So does this answer your question?
Thank you, sir. Thank you, sir.
Okay, let me continue. So I will not go into the details and describe all these functions. So the one important result is the binding energy and the length. So the binding energy is roughly up to a coefficient. I'm not sure if it is a coincidence or not. Up to a coefficient, it's proportional to the Casimir energy. That is just the central charge C divided by L. And this is the length. And one important thing is that this geometry is doesn't have a horizon, because we cut this geometry in the near horizon region and patched it to global ADS2. So there is no horizon and no entropy. And another interesting comment is that it's important that the binding energy turned out to be negative, because as I said, the traversable wormholes require negative energy inside. And this is related to my comment that traversable wormholes are fragile. Once you put too much positive energy inside the throat, it disappears. So whatever we put inside should be less than this binding energy. And it actually has a very nice information theoretic aspect. So suppose we actually want to send some information through this wormhole. Then we will be using quanta of roughly the energy of 1 over L, where L is the length of the wormhole. So this equation says that we cannot send more than the C2, the central charge bits at a time. So the total information inside the wormhole cannot be more than C2. And this corresponds to the fact that we cannot transfer more information than which can be, we cannot transfer more information than can be carried by this two-dimensional CFT traveling along the flat space-time. So, and in fact, we can even parametrically, it's the same, but there is a coefficient of 1 over 16. And actually, it would be interesting to kind of give a strong, to recover this 1 over 16 from some information theoretic argument. I believe it has not been done. And actually very similar bound exists for Gauss-Jeffreys wall protocol when you make the two sides of the thermophile double traversable for some short time by adding the double trace deformation. And in this case as well, you cannot transfer more than you need to actually produce this double trace deformation. So you cannot transfer more than it's already transferred by this two-dimensional CFT. Now let me move to the next part of my talk about the Randall-Sundrum type 2 model. So this model describes the following holographic setup. So originally it was proposed outside the holography, but for my purposes, I will mostly use the holographic interpretation of this model. So we have 5-dimensional Einstein gravity with a cosmological constant. And we have a ADS5 solution with a brane at finite distance. So this is one can verify that this is a solution where R5 is determined by this cosmological constant. So we have a brane at 10 with certain tension, which is also determined by lambda 5 at finite distance. So this is ADS5, and the brane is located at rho equals to 0. And holographically, it means that we have 4-dimensional CFT living on this brane, which is interacting with gravity, because this brane, it's located at finite distance, and so it has finite tension. So it's actually it supports dynamical gravity. So in the usual ADS CFT correspondence, 4-dimensional CFT does not interact with the gravity. And in this model, it corresponds to the case when we actually move this brane all the way to rho equals to infinity. So in this case, the tension is infinite, so the 4-dimensional gravity decouples. So this is so in short, this model corresponds to the holographic setup when the holographic CFT at the boundary interacts with the dynamical gravity. So this is just a very brief introduction to this model. And actually one neat fact is that if we assume that indeed our world is described by this, that by this model, that in fact we're living in 5 dimensions on this brane, then this model predicts a certain 1 over r² correction to the Newton potential. And the current experimental constraint from experiments with gravity at small scales is that R5 should be less than 50 micrometers. So if there is ADS5 out there, then it should have quite small radius. So I will actually use it later when I plug in all the numbers. So for our purposes, we will also add a U1 gauge field. So one can think about this 4-dimensional CFT as certain dark matter, which can be described holographically, and it has a gauged U1 symmetry. So we can have magnetically charged black holes in this theory, which are supported by this dark U1. So in the near horizon regime, we have ADS2 cross S2, but then the question is, how does the geometry look like in the bulk? So as with the usual ADS CFT correspondence, maybe I can draw a picture again. Usually in the ADS CFT, we have a boundary. So this is usually z equal to 0. In my case, this corresponds to rho equals to plus infinity. So in the usual IDS-CFT, we impose the boundary conditions exactly at z equals to 0. In my case, it will be at some finite distance. And it's wiggly, so it corresponds to some gravity. And then the radial direction is usually interpreted as a renormalization group scale. So near z equals to 0, it's UV. And deep in the bulk, it corresponds to IR region. And so we're actually asking the question, what happens at low energies? So what happens at low energies with this holographic four-dimensional CFT? One very nice answer is that actually it flows to ADS3 cross S2. So this ADS3 part says that effectively we will have a two-dimensional CFT in this case, because we have this ADS3 factor, and it has been described in the literature before. Is there a question?
Yeah, I'm sorry for the interruption, sir. Delta S5 is some U1 gauge field which is added at the brain, which is a four-dimensional object.
No, it actually it exists in the 5 dimensions as well. So these magnetic solutions. So it's a little bit tricky to find the solution with the ADS2 cross S2 at the boundary. So what one can do is one can start with R2 cross S2 at the boundary. So, sorry, maybe I should draw it differently. So this is the boundary. At the boundary, one can have R2 cross S2 with some magnetic field B. And then one asks how the solution looks like in the 5 dimensions. So one imposes one takes the configuration of this U1 field to have a constant flux along this S2. And then one imposes the ansatz that now this R2 part and S2 part, they have independent work factors depending on this coordinate rho. And deep in the bulk for rho, so in my case, rho is negative in this direction. For very negative rho, one finds ADS 3 times S2. Yeah, this U1 field, it lives in the 5 dimensions. So here the integration goes along the 5 dimensions.
Yeah, answer.
Does this answer your question?
U1 gauge field is added to make the solution ADS3 cross S2. I'm sorry, I'm not much aware with this. Of this. What does it mean? The solution flows to ADS3 cross S2. I'm sorry. You can maybe take up the question or not answer it, since I'm not aware of this literature.
So this ADS3, it has a scale it has two-dimensional scale invariance. So it essentially means that if I reduce my fields on S2, so what happens is that first I reduce S2 and then go to IR. In this case, it means that so I reduced on S2, so I'm concentrating on this part of the geometry, and I'm seeing that now this four-dimensional matter reduced on S2 will have two-dimensional scale symmetry. And I interpret this as an effective two-dimensional CFT. So something similar was happening just with the free fields without any holography. You can just find these fermionic modes in the background of a monopole. And once you go to length scales more than the size of this wave function on a sphere, then you can just forget about this inner structure and see that these fields, they are uniformly distributed around the S2. So if you just study their motion in the radial direction, one can describe it as a two-dimensional CFT. And in this case, but if the theory is a strong coupling, you don't have any conventional methods how to see the zero modes. And one neat fact that the same thing happens holographically. That we have this emergence of ADS3. And this is why I indeed can say that I have some two-dimensional CFT now, which travels between the black holes, and it will produce some Casimir energy. Yeah, I guess I should point out that we did not find the complete solution in this problem. So we did not find this bulk geometry in all the regions. So we essentially just studied two cases, ADS2 cross S2 at the boundary and just R2 cross S2. But finding the complete geometry, including the throat region, it would be very interesting. Yeah, perhaps one can do this numerically. Yeah, this is an interesting problem. So, are there any more questions on this?
Alexey, can I ask you once again for clarification? Sorry, I missed the last explanation. So this is a flow between ADS5 with boundary R2 cross S2 and ADS3 cross S2. Am I correct up to there?
Yes.
Good. And where is the ADS2 cross S2? That's the point I miss.
Okay. So good. One can erase this R2.
Okay.
And substitute it by ADS2.
Okay. So the ADS5 is foliated as ADS2, S2, and another direction, right? That's the asymptotics. That's the UV asymptotics.
Yes.
All right. And you flow in infrared to some ADS2 cross S2.
So in the infrared, it's ADS3.
ADS3 cross S2. Sorry. Yeah. Okay. Perfect. Thanks very much.
Yeah, but there is actually one subtlety. Because one has to choose a specific embedding of this ADS2 into ADS5. And I believe it's not unique, and we studied only some particular embedding, which I believe is true for the outside region. So because you know that extrinsic curvature of this embedding will determine the stress energy tensor at the boundary. And if it is vanishing, then it's easy to find this embedding. But the throat region, it will be, it should have some negative energy inside. So this negative energy, it should correspond to some very specific embedding of this ADS2 inside ADS5. So maybe this is why I draw R2 at first, just because this example is clear. But when you embed this ADS2 into ADS5s, there are choices. So we studied only one particular one, which respects the ADS2 isometries. But the Casimir energy in general will break this ADS2 symmetry, and this is why it will correspond to some complicated embedding. So this is something we did not do, and it would be nice to do this numerically.
Thanks very much.
Okay, I guess I have 10 minutes, but I'm almost done, in fact. So as I said in the beginning, for free fermions, these two-dimensional massless modes, they arise below certain scale, below a certain length scale. And the same happens in this case. So this ADS3 will emerge for energy scales at length scales above this magnetic scale. So LB is roughly up to some constants. Again, it's proportional to the square root of the magnetic field, square root of Q. So, and because we have ADS3, now we can compute this effective two-dimensional central charge using the standard relation, and it's equal to this. So this is essentially what we need. So now we just impose the constraint for human traversability. So it will be humanly traversable if the tidal forces are not too big. So we say that roughly we cannot have more than 20 G. And then the tidal force is very roughly, for an estimation, is the size of a person divided by the RE squared. And if we require this to be less than 20 G, then RE should be this big. And I believe it will fix, it will be some inequality for the 5-dimensional coupling constant G5. And apart from that, we also have this constraint that the radius should be less than 50 micrometers. And because of this, here the constraints on the length of the wormhole and the binding energy. So we plug precisely RE equal to this, 10 to the 7 meters, and R5 50 micrometers, then we will get that the length of the wormhole is some 1,000 light years, and the binding energy is big. So this is actually very important. It means that if we send a spaceship of mass less than this, the wormhole will survive. So both the wormhole and the human will survive. This is good. This is good, but there are issues. The main issue is this. So for outside observer, it will take this amount of time to see another observer travel through a wormhole. But if you compute the proper time, then it will take just less than a second for an observer to travel through. And it's related to a huge work factor between the flat space-time and this ADS2 inside. So this gamma is L divided by RE, it's 10 to the 12. It's a huge blue shift factor. And because of this, CMB and dust will be accelerated to enormous energies. So if you, for example, now ask what happens if I have a spaceship and the CMB traveling in the opposite directions, then in fact the relevant warp factor is gamma squared. So in fact, even the CMBs will be a huge problem if you actually want to go through. So the spaceship will have to sustain like this enormous energy flux. And even for this amount of time, it's a lot. So this is one problem of these wormholes, but in principle, this can be done if you shield it from the outside radiation. If you actually want to make it practical, but yeah, this is one practical problem of this. And also potentially, if we have some dust falling inside, and it can collide because of this huge boost factor, and the products might be at rest inside the wormhole and accumulate, and eventually it will destroy the wormhole. So the wormhole itself, it does not evaporate because there is no Hawking radiation, but dust and things like this might get stuck inside and eventually exceed this binding energy. So, okay, let me maybe summarize. So one can construct traversable wormholes in 4 dimensions using magnetically charged black holes and matter. It's stable against small perturbations because the geometries inside are essentially ADS and spheres. And they can be embedded into Randall-Sundrum model. And the current constraints of Randall-Sundrum actually, surprisingly, they allow the humanly traversable wormholes. I did not go precisely into the details of this phenomenological aspects of the Randall-Sundrum, but at least it makes sense. We don't have some huge number of free fields. They strongly interact as we expect, and if we describe them holographically, the corresponding radius of the curvature can be small. So at least there are no obvious violations of common sense. So there are many open questions related to this. Maybe the most interesting one is how to form these wormholes dynamically. And here the main problem is the entropy, because even near the extremality, 2 Randall-Sundrum black holes has enormous entropy, but the wormhole configuration doesn't have any entropy. So one has to come up with a way how to shed it. And moreover, in 4 dimensions, this involves a topology change, because we connect to space-time region and at the handle. So I guess, again, without UV completion, without a gravity description with a UV completion, we cannot describe this. So again, it would be interesting to see if we can describe this holographically. Okay, this should not be there. And finally, interesting question is how to detect them. So if these objects indeed exist in the universe, how can we actually see with a telescope that this is not just two black holes, but it's actually a connected wormhole. Okay, thank you very much.
Okay, Alexey, thank you very much for this very interesting talk. We already had some questions, but we have time for more.
what you mean, what you mean by topology change here is the creation of the handle that is the wormhole.
Yes, precisely.
I see. Okay. Thank you.
Sir, can you comment on where does the entropy for the near extremal black hole come from in the t going to 0 limit?
Yeah, it simply comes, so the standard equation, maybe I can go back. Yeah, the standard equation is the entropy by Hawking formulates the area of the horizon divided by 4G Newton. And in this case, when you go to near extremal regime, even if you go exactly to the extremality, when you compute this horizon area, it's non-zero. So I believe it's something just P times RE squared for G Newton.
Sir, I wanted to know of an intuition as to if you can ascribe some prescription of what is acknowledging this entropy, meaning can we address the question microscopically in the near extremal limit?
So you're asking where this entropy comes from microscopically? I think this is this is kind of a big question in quantum gravity, where this entropy comes from. So
do we understand where the entropy comes from in the extremal limit? So I just try to interpolate that to get to know about the near extremal limit.
So in the near, in extremal and near extremal limit, they are not that different. In the near extremal limit, there will be just some small corrections proportional to the temperature. So they are not very important. So perhaps the only answer I know comes from the string theory. There is a paper by Waffe and Strominger who embedded these wormholes into string theory, and this then this entropy essentially comes from the string excitations on the brains.
Okay. Thank you, sir.
May I ask a next question?
Yes, please.
So there are some geometries like extremal vanishing horizons, such that in the extremal limit, the ratio of entropy over temperature is fixed, but both of them will go to 0. I was wondering if you have thought about using such a geometries to.
No, actually, I have never heard about these configurations. Can you maybe provide a reference for them?
Yeah, sure. There are some works by Gobser and also some works by Shahin Sheikh Japari and Daniel Grumiller, I think. Mm-hmm. So it's like this. If you have maybe charge in your system, once you want to take the extremal limit, you take the limit. I mean, you also play with that charge or with the radius of one of the direction, such that once you take the limit, the entropy is also going to 0. That charge or that radius also vanishing in somehow. I think there were 2 papers by Gobser, if I remember correctly, and a couple of papers by Sheikh Chapari and Gromger.
Okay, it sounds very interesting. Yeah, I should
Yeah,
definitely.
and it's called extremal vanishing horizon. I mean, if you Google this, you should find this. Okay, because it seems that it's kind of important for your setup, right? To have that.
Yeah, well, it is not important to actually in finding the solution. It might be important if you want to actually see dynamically what happens.
Yeah. Okay, thank you, sir.
Any other question? Okay, if not, we thank Alexey again for this very interesting talk.